Advanced Financial Modeling, Topic 7, Option Valuation and Hedging, Learning Objective number 4. We're going to review moving average volatility and EWMA volatility. So in the next topic, we can learn another vol model called GARCH. So estimating volatility is the central problem in option trading and option valuation. Especially if you believe in the Black-Scholes model, it is the one input that you need to value the option. So we've had a couple things we could do with volatility to give it a better idea of what standard deviation can be, besides just looking at, say, a full sample standard deviation from the last 2 to 5 years. One is doing a end-day moving average volatility, MAV, to see what's volatility been over the last 2 years in, say, 20-day segments, 20-day subsamples. Gives you an idea that, well, over and looking at any 20-day period, it's been as high as, say, 20 or and low as 10 or something like that. We're going to show in the next spreadsheet, even though we're going to do a subsample, say a 20-day volatility, where it's always convenient to annualize volatilities. Almost any time you ever see a standard deviation or volatility in finance, it's an annualized number, even if you're talking about pricing a 1-week option. So the following worksheet computes the 20-day moving average volatility for Google over a longer time horizon. And we'll go to the spreadsheet and look at this. And so you can see we have data here from 2010 to 2012. These are Google prices. And then I have Google daily returns. And what I do with that is I calculate a full sample standard deviation using the STDEV function times the square root of 252 to annualize it. So over that 2-year period, volatility was 29.08%. However, if I just look at the last 20 days, it's been running on an annualized basis 14. So if you're trying to price an option that matures in the next, say, 20 days, do you use 29%, what it's been running for the last 2 years, or do you use 14%, what it's been running for the last 20 days? And by just keeping that formula and copying that down, every data point in this column is a 20-day volatility. And so when I graph that 20-day volatility, even though the standard deviation over the long term there, the full sample average was 29%, you can see it was as high as looks like 60% and as low as 10%. This makes option valuation really difficult because what are you supposed to use? And in that last data point, it's been running 14. Makes me really uncomfortable of using 29. So that's using a moving average volatility. Let's talk about EWMA volatility. What EWMA does, we'll go back to this graph and talk about EWMA. When you calculate the standard deviation over this full sample, what it's doing is it's using these returns and taking the squared deviation from the mean, the average squared deviation from the mean, and it's treating every day equally. EWMA, it's going to use the squared deviations from the mean. However, it's going to use this data a lot more than this data, in particular what it's been running lately. So it's a weighting scheme, an unequal weighting scheme, to calculate the weighted average deviation from the mean. So we did this in an earlier topic, that the standard deviation formula is the square root of the variance, and variance is the average squared deviation from the mean. So if I had, say, n observations, say 200 observations, I would take 1 over 200 times each observation, and that would be the return on that period minus the mean times the square, or to the second power to square that, and that will give me an average square deviation from the mean. And when I take the square root of that, that gives me standard deviation. And research has shown that maybe I shouldn't be treating what happened 2 years ago the same as what happened yesterday. Research has shown there's volatility clustering, or also called autocorrelation of volatility, meaning that if yesterday was a really big move in a particular stock, tomorrow it's more likely to be a really big move. And if today was a small move, it's more likely that tomorrow will be a small move also. There's clustering of volatility, or there's autocorrelation in volatility. You can think of it as calm follows calm, and volatility follows volatility. So that EWMA is a way to compute that. And we did this before. EWMA takes this standard deviation formula, and all it does, it replaces that equal vector of weights, say 1 over n, with a different vector of weights, which is right here. And that is using this 1 minus lambda times lambda to the I minus 1, divided by the sum of all those factors to ensure the weight's equal to 1. One other thing we often do in EWMA volatility or other volatility measures is often when we have daily data or weekly data, sometimes we'll just say, you know what, the daily mean's pretty close to 0. So when I do that, I can just do return squared and not return minus 0, return minus the mean squared. So it's very common when you have daily data. It's just assume a daily mean is 0. And then where do those lambdas come from? Well, they tend to be between 9.9 and 0.99. And all it means is when the lambda is approaching 1, it's closer to equal weights. And when lambda is lower, it is more unequal weight. You're weighing the more recent data more heavily. So let's take a look at this spreadsheet here. It calculates EWMA volatility. And again, I have my 2 years of Google prices. I have the squared return. We can think of that as the squared deviation, the squared deviation from the mean, since we'll assume that daily mean was 0. And then I do my 1 minus lambda times lambda to the I minus 1 factor, and I use a lambda of 0.94. I then sum up all those 1 minus lambda times lambda to the I minus 1 numbers, and then I do my final calculation of squared deviation from the mean. I take that weight, that's 6% right here, divide it by the sum of all those weights. That makes sure that those weights equal to 1, and I multiply times the squared return, or the squared deviation from the mean. So this is a weight times a squared deviation. Each one of these is a weight times a squared deviation. If I sum all those up, that's the weighted average squared deviation from the mean. That is the daily variance using EWMA, the daily variance. If I then take that and I take it to the 1/2 power to make it turn it into a standard deviation, and I multiply times the square root of 252, I now have an EWMA volatility, annualized EWMA volatility, and it turns out to be 22%. Now watch what happens when I change this lambda to 0.9999999. EWMA winds up giving you the long-term average. Remember, the long-term average is right around 29%. So the lower that lambda is, or the farther it is away from 1, that means that the weights it's weighing the more recent data. Look what happens when I change the weight lambda to 0.5. Notice the weight on yesterday is 50%, the weight on the day before 25%. So you can see it's really just using the last few days. When I make it 0.94, it's weighing the last day 6%. So it gives you an idea of EWMA. And if I go back and I look at my graph, we said the long-term average was 29. It's been running 14, and EWMA is giving me 22. So that's the idea of EWMA. So in the next topic, we're going to talk about EWMA a little bit more, and then introduce a new model, GARCH, which is probably the standard model in finance to estimate volatility, especially for pricing options of different maturities.